been talking about AI the entire day, and I think we've kind of skipped over a very important part of AI that maybe doesn't get the attention that it deserves, which is the data side of AI and how much data it consumes and it requires to actually make the systems work. And it's quite evident we're in the age of AI. But actually, if you look at the graph here, you realize we're pretty early in this age still. This is an exponential graph, and we're almost at the beginning of it. By the end of this decade, the market is supposed to be close to 1 trillion, which is simply immense. Um, but as I mentioned, we're still early in this AI revolution. Kind of a bit like how we were in the mid 90s during the internet revolution, back when it used to be a little bit difficult to put a website out. If you wanted to put a web system out there, you had to buy servers. And if on Sunday your website was supposed to receive more clicks, you just had to go out and buy more servers. Today you just go to AWS and you have auto scaling enabled. It's a bit like that in AI as well today. Um, Moving AI systems into production is not that easy. It takes a lot of effort, which is why even though AI systems seem to be everywhere, almost 85% of AI systems that are taken on in any organization don't end up being in production. They end up failing. At different stages of their progression, somebody somewhere decides that this is not going to work out, and they don't make it into production. Um, so one reason, as I mentioned, is that we're simply very early in this age of AI. People still haven't quite figured out how to make AI systems work and how to implement them such that people actually want to use those AI systems. Um, the other side is what we call the long tail problem. So essentially, if you look at the business value here, the most business value is created by a very small number of AI use cases. Use cases like speech recognition, your recommendation systems, your facial recognition. These are cases that everybody knows and they've probably used. And they're so popular and they create so much value that a lot of effort has been put into these use cases, which is why there's a lot of research around it. There's a lot of available models and systems around it. Um, but the reality is that most of the use cases that we find in industry don't fall into that category. They are smaller use cases that probably don't have individually as much value, but they are the ones that people are trying out the most. And these are your medical use cases, perhaps trying to pre-screen for a rare disease, or for example, trying to figure out manufacturing issues. So, and because these don't create as much value as the other ones, there's little academic work done on them, and which is why it becomes even more difficult to implement them for production. Um, the other problem with these long tail problems is that they simply don't have enough data. We've come across situations where people had as few as 100 examples for each category that they wanted classified or they wanted identified. And the problem is that all of the models and all of the systems that we have currently available, they are not supposed to work with these few examples. They're supposed to work with millions and millions of images and hundreds and thousands of hours of data. And they don't work as well on these smaller use cases. Um, there's just one more problem, which is a kind of disconnect between academia and the industry. And this was actually presented by Andre Karpathy on one of his Tesla talks. And this shows the focus of people in academia and the industry. So when you're a PhD student or you're doing some research, your your aim is to further the foundation blocks of AI. So what you are trying to do is you have some baseline data sets that are used across the academia, and you try out different combinations, different algorithms that work well on those baseline data sets. But that is not how the industry works. In the industry, you have to work with real data such that the model actually works. And that's where the kind of disconnect is, because you can have very good state-of-the-art results in research papers, but when you actually try to implement them for real-world problems, they don't work as well. So that's where the idea of data-centric AI comes in. And the idea essentially is that in the industry at least, instead of focusing on trying to develop new algorithms and trying to refine the algorithms that are already out there, you try to focus on the data. Because the idea is that, at least for some of the most popular use cases, your facial recognition, your speech recognition, the models that are available out there are actually pretty good. And you don't really need to make a lot of changes in them to make them work. You can pretty much pick some of the models from GitHub and make them work without actually making a lot of changes. You might have to make changes in the production to make them more efficient, but you don't have to really make any changes to get more out of them. But what you do have to do is invest significant amount of time in the data side of the things. And this is what kind of highlights this disconnect, which is that AI, unlike traditional computer science, AI is a combination of both data and code. So for example, in the traditional computer science paradigm, if you, for example, tomorrow came out with a new sorting algorithm, all you would need to do in your system is replace your current sorting algorithm with a new algorithm and it would work on any new data that you throw at it. But that's not the case with AI systems. If it works on one kind of data, it is probably not going to work on another kind of data. So that's one of the disconnects. So when we talk about data, a lot of the times the first thing that comes to your mind is, well, we need more data. We don't have enough data to do something. And that's what data-centric AI probably means. But that's actually not it. What we want to focus on is good data, not bad data. And what that means is, instead of simply accumulating more and more data, you need to look into your data and figure out where it's going wrong. And one way to look at it is that if you have 1,000 hours of data set, it kind of acts like a band-aid over the actual problems that exist in your data set. So having lots and lots of data will put a band-aid over the issues that you have, and it will work, but it will just cost you more. It will cost you more in time. It will cost you more in money. One of the other things is, so these are examples from some of the most popular publicly available data sets that are widely used in academia. ImageNet is probably the most widely used image-based data set. MNIST as well. Amazon Reviews is a huge text-based data set. And all of these have huge amounts of errors. In fact, ImageNet has close to about 7% error rate, which is huge for a data set that is used as baseline in research papers. And the reason is that it's just not as easy to create good data. And what we're trying to do is we're trying to define what a good data set is. So the first thing is you need to have a consistent and accurate labeling of the data. And as it turns out, even that is not as easy to do. So for example, this is an example of one of the actual use cases that we encountered, where we had to figure out, where we had to label cases where these laptops were defected. Now, in the first and in the last case, it's pretty easy to see that these are defected. There's a pretty bit, the first one is not defected, the last one is pretty easily defected. But different people would look at the middle image, and some people would say it's defected, some people would say it's just a scratch. Others might, in some situations, some people might confuse it with the lighting situation as well. So it's not as easy to label things consistently and accurately. So the solution is actually pretty cliched. The first one is that you simply need to invest more time when you lay down instructions for how to actually annotate your things. And that means that you go over all the possible conditions that your data can go through, all your different labels, the different situations those labels will encounter, maybe some edge cases as well, and you need to go over them iteratively. So for example, you create a document, you send it over to your labeling team, they come back with some issues, and you again make changes to them, and it goes iteratively. One other solution is, if you have a lot of time and if you have a higher budget, is to simply get each or some of the data points labeled by more than one people. And then you see which data points, on which data points do labelers do not agree with each other. And then you see and analyze those and figure out why it is that these are not getting labeled properly. And you go back to your annotation instructions and change them slightly so that it's more easy for the labelers to label it. Or if you can actually get all of your data labeled by more than one people, then you can simply use voting to see which label should be accounted for each data point. The other thing that defines a good data set is also data diversity. So for example, if you have 1,000 hours of data set, but let's say 900 of it is very similar to each other, it's not really contributing to your model. So you might have a huge data set, but it's really not indicative of what you actually want to solve. So your data should be representative of the kind of problem that you're trying to solve. The last point is you need to take care of edge cases. And edge cases are situations that don't normally occur, but when they do occur, they're catastrophic to your AI system. So for example, in this case, a self-driving car might be tripped up by the fact that there's a car drawn on a bus. So how would the system react? So you need to first see how your system reacts in such a situation, and then you need to figure out how to solve this problem. This is actually a very popular problem in the autonomous driving community, where there was this autonomous car that used to stop every time it used to cross this area, because the signs here resemble the stop sign in the US. So it was mistaking it for a stop sign and stopping by every time it used to pass by. So this is another example of an edge case. So how do you solve for edge cases? Well, whenever you're trying to create a model, an AI system, the first step is always to collect data, right? So you collect your data, you label it, you train a model on it, and then you test on the data and figure out where it's failing. For example, in the previous situation, you would do a dry run of the car or of your self-driving vehicle, and you would see in which cases it is failing. And if you figure out that in the cases that it failed, the issue was that we simply didn't have enough examples for it. For example, in this case, the situation might be that you've just never encountered such a situation before. So in that case, the ideal scenario would be that you go out and collect similar data. In other cases, it might be that you have the data that resembles these cases, but they were simply not labeled well. So then you would go back and label the data again. So lastly, I would like to point out to something that we've been working on for almost the past year, which is the concept of active learning. And so usually when you're creating your AI system, you're training your AI models, what you do is you pick all of your data and then you randomly create batches out of it and you feed it to your data model, feed it to your AI systems, right? With active learning, the idea is that if you can prioritize the data, or if you can create a queue of data, then you can actually optimize how your models learn. So as an example, this is, if you guys are familiar with the DALL-E system that OpenAI created for image synthesis. So what they did was that they had a few of the images labeled, they created a classifier out of it, and then there was an active learning algorithm that was selecting the data that the model should next train on. So instead of randomly picking any of the images that they have, millions of images, just picking any of them, the images, they chose which ones would optimize the training procedure and fed them to and sent them to the human labelers and only got them labeled. And this reduced their training time and cost by almost 30 to 40%. So here's the idea with active learning. So you can imagine this graph to be representing how well an AI system is learning over time. So what this is essentially showing is on the x-axis you have how many labeled data points you have, which is roughly equivalent to the data set size that you have. And what you see is that the blue line is essentially your normal learning curve. So you start to learn very steeply, and then as you see more and more data, you start to saturate, and eventually you plateau over it, right? But sorry, the dash line is what you normally see. The blue line is what you see with active learning. So what you're seeing is that with the blue line, you're getting to almost the same amount of accuracy by around 3,000 data points, whereas with the normal random sampling, you're getting to that same level of accuracy, of efficacy at about 7,000. So essentially, you could have stopped training at about 3,000 or perhaps by 4,000, and you would have got the exact same system. So that's the idea with active learning, that you reduce the amount of data that you have to train to get to the same level of accuracy. So that's essentially it. So what I was trying to highlight is that data is a very key aspect of your AI systems, and algorithms are fine. They're very essential. But if you really want to make your systems work in the real world, you have to focus a lot on the data as well. Thank you.